Hello, everyone. Good morning, good afternoon, good evening, depending on where you are in the world. Welcome to this third in the series of free webinars conducted by Second Quadrant. Today, we are joined by Pavan Deolasee, who is a senior member of the Second Quadrant team and a respected community contributor to the Postgres database. He'll be talking about the power of indexing, and he'll be talking about it for the next 45 odd minutes. In case anyone has any questions during the webinar or after the session, there's a questions tab to the right of your panel. You can enter your questions over there, and we will try to answer as many of your questions as possible towards the end of the webinar. So without further ado, I will just hand it over to Pavan.
Thanks, Umair. Hello, everyone. I hope you can see me and see the slides as well.
Yep, you're visible. Thank you.
Okay, cool. Okay, so the topic of today's webinar is power of indexing, and we are going to cover some details about various indexing strategies that Postgres offers. Before we do that, I would like to briefly introduce myself. I work with Second Quadrant, and I've been part of Postgres community for more than a decade now, having contributed many features, bug fixes. I'm also the primary developer committer and maintainer of the PostgreSQL project. I'm also part of the team which is organizing PGConf India for last few years. So if any of you are from India, I would encourage you to be part of this conference next year. So that's the agenda for today. What we are going to do is we are going to primarily talk about various access methods in Postgres. And when we talk about the access methods, the heap is the sort of the most primitive access method. We will see how heap is structured in Postgres. We will go to we'll try to cover some internals of B-tree indexes because they are the most widely used and popular indexing scheme. Brain indexes, which are new to Postgres, will have some details about that, and then overview of other few indexing strategies like hash indexes, gist engine. I'll try to provide some brief information about when you are managing a database system, how do you find missing indexes or unused indexes, and what are the implications of these things. And towards the end, we'll take some question and answer, as Umair just said. So let's talk about the most primitive way of accessing data. And heap scan is, as I said, is the most primitive access method. So when you insert data in a table, what happens is your table is it's at the file system level, it's represented by one or more files. Each of these files is 1 gigabyte in size, and the file is divided into blocks. The typical block size is 8192 bytes, though you can configure it if you want, but we don't need to get into those details. Now, what happens is when rows or tuples are inserted in a table, every tuple gets an address, what we called TID, or tuple identifier. It is the physical location of tuple within the table, and typically identified by a block number and an offset. Now, block number is pretty straightforward. Um, it's the sequence of that particular block in the physical storage. And when I say sequence, it did not mean that because the table may have more than one file at the file system level. So this is a logical sequence number within whatever file that the block is currently residing. The offsets, on the other hand, is it's an indirection pointer within the page, so that you can from external world you can quickly uh, identify a physical location. Yet the database has flexibility to organize things within a block. So that's what TID is made up of. So when you insert rows in table, initially all rows are stored in the order in which you inserted, but that ordering may change as you update or delete tuples within the page. So if you do deletes, inserts, updates to your table, be prepared to handle the case where the initial ordering of data is no longer true. So I've given a simple example of how tuples are stored uh, in a table, right? So, for example, a tuple with city Pune has a TID 0, 1, whereas Kanpur is stored in block number 1 and at offset 2. So with that table structure in mind, when you want to access your heap data, what you can do is you can sequentially scan the table. For example, let's say you are looking for a city named Nagpur, right? The easiest way is to scan through the entire table, look at each row as you scan, and see if that row has a city named Nagpur, and if it is so, then return it to the column. Now this is not obviously very efficient, because you are going to scan the entire table every time you want to look for a row. But at the same time, remember, sequential scans are not always bad either, because a good thing about sequential scan is that it reads the disk, in a sequential manner. And while things are changing, still sequential scans are much faster as compared to random scans or random access to the disk. So sequential scans is still a pretty useful accessing method. It is also very useful when you got a small table, or when you are selecting from selecting majority of the data from the table. And in both these cases, also sequential scans could be could be beneficial, and we'll see why is that when we look at the index structures in more detail. Um, So yeah, I mean, sequential scans are great because they are simple. They read file in a sequential manner, or when the table is small, or you are selecting most of the data. But what if your table actually consists of millions of data blocks, right? And then you are looking for one particular row in that table. Um, for a representation, I have sort of uh, created that diagram. It's this particular table as shown is not very large, but imagine that it's a pretty large table, and you are looking for one row where say city is Kanpur. So it's not practical to scan the entire table, maybe hundreds or millions of blocks every time, just to seek one row. So what do you do? I mean, the clear answer is to build index on such a table. so that such queries can be benefited. So what is an index? I would define index as a secondary table that you create in addition to your primary table. And this secondary table, it stores and maintains some key information, and it maintains in a manner so that you can very quickly search for particular information in the main table. And not only search, the structure or the secondary table should have enough information or mechanism so that you can then retrieve the remaining data from the main table. I gave this sort of example here, and we probably all know from our school and college days there we used to have an index printed at the end of a book, right? And whenever we want to look for any technical term or information, what we do is instead of scanning the book every time and looking for that particular word, we look up the index at the end, and then what that index has is, it will tell us that this particular word appears in these many pages, or these particular sections of the book, and then you can go and look up that particular section or page very quickly. So book had or has word and page. What we have in database is key and a pointer. So the database would tell you that for a given key, uh, what are the places where you can find this particular key. So that's the basic structure of index. Irrespective of what sort of indexing method is used, that's sort of a very high level summary or architecture of any indexing method. So what are the index types that are supported in Postgres? As I said, B-tree indexes are the most popular common index types because they are very versatile, and they can solve many common problems. They are also the default index types in Postgres. So if you just build an index, if you say create index on some particular table, you'll end up having a B-tree index on that particular table and column. But there are other types of indexes as well, like hash indexes, block range indexes, or what we call brain index, and gin and gist. These are some of the most common index types supported by Postgres, and each of them they serve a particular purpose, and we'll see as part of this webinar what are those purposes that these different indexes solve. Uh, we are going to have more focus on B-tree indexes, as I said, because they are more common and popular. So what is a B-tree index? It's a tree, and in computer science, when we say it's a tree, we typically mean that every branch has the same height. So B-tree is created and maintained in a way so that the height of the B-tree remains the same for every tuple that is stored in the tree. Uh, and the good thing about this sort of characteristic is that the retrieval time for any record in the tree, it remains the same. I mean, same in a sense, it's relative to other tuples in the in the index. You'll spend same time looking up that particular key value. The keys in the B-tree indexes, they are sorted and ordered by the key on which you have built the index, and every index tuple in the B tree, it contains the key and pointer to the main table, or what we call heap in Postgres. So the B tree index would contain key value and the pointer to the heap. Uh, so let's with that sort of high level view of B-tree indexes, let's look at an example and see how indexes would typically uh, help. Now I have created a table here named EMP, and it has just two columns, ID and city. Let's assume so. Um, and there are no indexes right now. Let's say you run a query on this particular table. You say select count star from EMP. Now, there is nothing for planner to choose from, or executor to do, because there is no secondary structure or additional information or summary information that has been built on top of this table. So when you run this query, the only method that database knows to retrieve information from this particular table is to scan it, every time. Now, irrespective of whether you do a count star on that table or whether you look up a particular record with ID equals true, if you look at the second query, it's a selection query, point query, whereas the first query is an aggregation query. But in both the cases, the only thing that the planner knows is to scan the table in a sequential manner. Now, let's build some indexes on this particular table. So I'm building two indexes. One is, an index on column city, which is not unique because, multiple employees may share the same city. Uh, but we also build, say, a unique index on column ID, which is known to be unique in the, uh, in the table, because that's how, say, application generates and inserts row in this particular table. So you know that you not only know that ID is unique, but you also want to enforce that. So you create an unique index on column ID, and because you want to run queries on column EMP, you also build an index on EMP column. So I built indexes on these two indexes on the table, and now rerun the same query that I had run before. Um, I'm doing a point query on city name Nagpur, and then also running a point query on the other column, which is ID equals to 2. Now Nagpur is not it's not unique, but we have an index on column city, whereas ID is unique, and we also have an index on ID. But if you look at, even after we built indexes on the table, the planner is still choosing sequential scan. And this is, a mistake some of us make quite often, and uh, we, we think why my database is not using an index that I just built. The missing part here is, even though we have built the indexes, the planner doesn't know, doesn't have enough information about it yet. So what we are missing is a step called analyze, which so analyze is the command in Postgres. So you say analyze EMP, and when we do that, the database builds, planner stats for that particular table, and it will sample the table, read some blocks, using some algorithm, and try to create enough information about the table. Like for example, when we ran analyze on EMP, it would have noticed that there are no duplicates for column ID, or there are duplicates for column city with, say, certain values appearing so many times. Obviously, we don't scan the entire table during analyze phase, but actually take random samples and extrapolate to sort of guess the planner stats. Now we ran analyze, and then we again ran our original queries. But if you notice that it still hasn't chosen index scans, it's still doing sequential scan on the table, even though now the planner knows about the presence of index, as well as it knows that column ID is unique. So it should ideally use um, index scan for the first query or even the second query. The reason why it's not doing is that my EMP table is very small. I inserted only handful records, maybe 10, 20 in this table. So when the table is so small, the planner would sort of guess, or it would come to a conclusion that I should better do a sequential scan on the table, because even if there is an index, going via index um, is not efficient. But if I actually now insert a lot more rows into table, so I truncated away the table, and this time I inserted 10,000 rows, uh, and I have added another column in the table, basically just to make the rows wide, so that it occupies a lot more blocks. So with 10,000 rows in table, and another analyze on the table. Now, if I run my queries, you would see that it's now using the index. The first query is doing an index scan on EMP, because now Planner figures out that I should better go via the index path, because that's the most optimal way to retrieve information for employee with ID2. Uh, so that sort of first query is now pretty clear, and why it's doing index scans. The second query is a little curious again, because I would like to spend a minute talking about it. If you see that even though we have an index on column city, instead of doing an index scan, what the planner is doing is, it's choosing to do a bitmap index scan followed by a bitmap heap scan. And the reason for this is that the column city is not, there are many duplicates for this particular column. And if there are so many duplicates, in this case, there are only 25 cities. So there are about 400, duplicate values for each value of column city. Then doing index scan doesn't make sense, because even though you can retrieve all the 400 uh, in TIDs from the index, to fetch those 400 rows, you will have to do a random access scan on the heap, and that's not very good. Instead, what now we are doing is we are using the index, and we are using the index to find the blocks where these values appear, and then using that information, then we do a heap scan, and that heap scan now scans the table in a sequential manner. This is sort of important to understand. Sometimes we see confusion, like even if I have index, why it's doing heap scan. It's doing that because it's cheaper to retrieve rows uh, that way. Let's look at now, B tree internals. So there are leaf pages. As I said, B tree is a tree structure. When we draw the tree, we draw the root at the top, and then there are branches, and then leaves at the end, at the bottom. So the leaf pages, which are at the bottom of the tree, they actually store the real information about a particular key, and which heap tuple actually has that key. Whether it's if there are duplicates, then the index will have duplicate values. If this is a unique index, for any given key, you'll have just one index tuple. So you have this information in the leaf. For example, city Bhopal index says appears in tuple 2 comma 3, which is the block number 2 offset 3. whereas Delhi, it is in block number 7 offset at offset 3. And these leaf pages, they are linked by previous and next pointers, so that you can go from one leaf to another quickly. You would also see that the all the tuples in a page are sorted by the column on which the index is built. The index itself doesn't contain any visibility information, and we probably don't have time to talk about visibility. But Postgres uses something called as multi-version concurrency control, and there could be multiple versions of a tuple in the heap, and visibility information tells us which version we should be looking at. But that information is in the heap, and B-tree doesn't maintain any of that. So yeah, I mean, this is probably more, uh, I would say a picture which is one level deeper. It's now showing the index leaf, and it's also showing the the heap pages. Obviously, I haven't shown all the index tuples here. There would be a for example, I have only shown Agra, but there would be a tuple, index tuple for Madurai as well. But that's the idea. You have index leaf, and then you have which contains the keys and the pointers to the heap. Whereas heap would not only contain key, but any other additional information in that particular row, other columns in that row. This is how the B-tree leaf pages are linked. As you would see that each page is sorted within itself, and then the pages are linked together so that you get a logical ordering between all these pages. For example, the first page would never link to the page, the third page. It will always link to the second page, because that's how we preserve the logical ordering. Uh, So this is a picture where I have now basically taken the heap out of the picture. So this is the the smaller boxes are the leaf index leaf pages. But in addition to the index leaf pages, what we have now is also an index non-leaf page, which you can consider it as an index on top of index, right? So it is telling you that which index pages contains which values. For example, anything smaller than Ghaziabad is in page 0, whereas anything between Ghaziabad and Lucknow is in page 1, and so on. So the as the size of the index grows, as there are more than one leaf page, you'll start putting you know a parent page which summarizes information for the leaf pages. And then this is sort of the complete picture, and now you have a root block, then you have non-leaf pages, and then you have leaf pages, which then in turn point to the actual heap. And in addition to all of that, there is also a meta page, which is sort of it helps us quickly find the root page. Now if you look at this complete picture of B-tree index, you would see that to retrieve any value from this index, you would have to do at least 4 block reads. Even if you assume that the meta page and the root page are always cached, you still have to do 2 block accesses to get to the actually the index tuple, and from there you have to then go to the heap, which means doing another block read. So with this complete picture in mind, you will now understand why sequential scans on very small tables are usually cheaper than doing an index scan, because with index scan you are not uh, querying just or reading just one block. You actually have to do have to read multiple blocks. Um, so yeah, I mean that sort of explains why sequential scans are not always bad, and why planner chooses to use them for very small table. You would also notice that the internal B tree pages or non-leaf pages, they are also linked by previous and next pointer. So let's see how equality search works in a B tree. For example, let's say you are looking for a city called Nagpur. And I'm sorry about using all Indian city names here, but they are not very hard to pronounce. So let's say you are looking for a city called Nagpur. What would happen from meta page will come to the root page because that's where the search always starts. In the root page now we have two tuples, and we see that anything which is greater than or equals to Lucknow has to follow the down path. So that's why we go from Lucknow to the second non-leaf page. Uh, in that non-leaf page, now we know that anything between Lucknow and Surat can be found in the first link, whereas Surat and greater than Surat would have been found in the second link. So then we follow the path and reach to the index leaf page. And now within the index leaf page, all the tuples are again sorted. So we can use a binary search within the page to find the tuple for city Nagpur. And once we find that tuple in the index leaf page, then we can use you know the information stored in that index leaf or index tuple to actually fetch the required heap tuple. So that's how the equality search sort of progresses in B-tree. Whereas if you're doing a range search, which is also another pretty powerful feature about B-tree. uh, so let's say you are looking for a range between cities which are greater than or equals to Nagpur, greater than or equals to Jaipur, and less than or equals to Nagpur. So you first, what you do is you start your search with for city name Jaipur, and just like we understood in the previous slide, we'll follow the index pointers from the root to non-leaf pages and then to leaf pages and find the index tuple for city Jaipur, and then fetch the heap tuple and return it back to the caller. But for the subsequent tuples, we don't have to really repeat the index search. Instead, what we do is because we know that the tuples within the index page are sorted, so we can start reading from Jaipur, keep going, once you exhaust all the uh, index tuples in the leaf page, we use the next pointer between the leaf pages, and we go to the next leaf page and again start reading from the start. So we start, we read Lucknow, Madura, uh, Mumbai, Nagpur, and since we have to end our search at Nagpur, as soon as we find a tuple which is greater than Nagpur, we'll stop and say that all the required tuples now have been retrieved. So that's how a range query or range scan work with B-tree indexes. So B-tree indexes, to summarize, they are default index types. They are pretty good when you want to do, equality queries. They are very good for range queries. They are also very useful for prefix matching queries, right? Because since the index tuples are all sorted, if you want to look for city names which start with letter AM, you can use B-tree indexes. Also, if your queries include order by clauses, since the index is already sorted by that order, you can use B-tree index to retrieve those tuples without doing an additional sort phase. Next, I want to talk about expression indexes. Now, we looked at the B-tree index, but what if the information in the index, or let's say people have entered value with mixed cases, right? Someone has used Nagpur in all capital letters, someone has used it in all lower cases. And if you want to look up, you know, all rows where basically city name is Nagpur irrespective of its case. So you want to do a case insensitive search, and one obvious way is to do, say lower city equals to Nagpur in all lower cases. But again, you'll see that Planner has now reverted back to a sequential scan because it doesn't know anything about this expression lower city. It knows that there is an index on city, but there is no index on lower city. And that's when you can build an expression index. So instead of building an index on city on column city, now you can build an index on an expression on column. So you build an index on lower of city instead of just city. And once you build this index, and now if you run the same query again, you would see that now the index is being used. Obviously, we are still doing bitmap map index scan followed by bitmap heap scan for the reasons that we earlier understood. But now at least the indexing is being used. So you can define expression indexes. You can use user defined functions in the expressions. You can use math functions, but the only thing that you need to be careful about is that all these functions and expressions should be always immutable. That is, they should always return the same value or same result for the given input values. And the expression indexes are only useful when the where clauses in the query also use the same expressions. Um, The next category is what we call partial indexes. Like for example, let's say you are not interested in indexing everything in your table, but you know that my queries are only going to look up for certain information. So why build index and maintain an index on all rows? Instead, what you can do is while creating the index, you can specify a where condition and say that index rows only those rows which satisfy a certain where clause. These indexes are much shallower and smaller because we are not uh, indexing every tuple in the table. So that's why the selects can be quicker. Also, there is less overhead when you insert rows or update rows because we can skip um, many rows while doing index insertion. So that's why partial indexes are very useful. And here is an example. Let's say if you know that you are only going to query um, employees in 4 particular cities, and you don't care about rows with other city names. So what you can do is you can create the same index on column city, but you can also add a where clause saying that only index rows if the city is in these 4 values. And once you do that, the index is still used when you query uh, for one of those cities. Like in this case, if you query for city Nagpur, which is not sorry, um, which is not indexed, the planner will do a sequential scan, whereas if you query for city Mumbai, it will do an index scan. Index only scans, these are also pretty interesting and powerful. Um, and basically, the concept is that if your index has enough information to satisfy your query, why even go to the heap? For example, we have a index on column id, and if you are only interested in basically fetching column id, uh, we could skip we could not go to heap and return the information from the index itself. Now this is a very simplistic example, but imagine you got an index on say 4 or 5 column. It's a multi-column index, and those are the only columns that you are choosing. Uh, then you can satisfy your query from the index itself. Now it's there is some catch to that, because as we earlier, sort of, I touched upon that the index doesn't have any visibility information. So that's why the heap and the index has to be in a certain state for index only scans to be useful. And usually what that means is your table, if it is static and has been vacuumed, then there are greater chances that index only scans will be useful. Um, that's all about B-tree indexes. It has already taken a lot of our time, so I'm going to go through some of the other things that we want to cover. Block range indexes or BRIN indexes, these are very recently introduced index types, and this index is very powerful and useful when you have extremely large tables, and you basically don't want to index the entire table. Instead, what you can do is you can build a summary information. For example, for a range of blocks, you can build summary. What is the minimum value and the maximum value uh, which is available in this range of blocks, so that when you later query, and if you are querying within that particular range, you know that you should visit these particular, or you should scan these particular heap blocks. Now, since the exact TID is not stored in the index, these BRIN indexes are always lossy. So you have to do a recheck after you fetch tuples from the heap. But the good thing is, there is no vacuum overhead for BRIN indexes, because you don't have to maintain them with accuracy. So this is an example of BRIN index. Again, coming back to our previous table with city names, what we are now doing is, in the block 0 of the heap, you would see that the smallest tuple is with city name Agra, and the largest tuple is city name Vadodara. Obviously, we are assuming that these cities are lexically sorted. So in the BRIN index, what we'll say is block 0 contains tuples between Agra and Vadodara, whereas block 1 contains tuples between Bhopal and Visakhapatnam, and block 2 contains tuples between Jaipur and Surat. So if you are looking for a city named Vadodara in your query, and if you have a BRIN index on that table, you can completely skip block number 2 and 3, because you know that these blocks, they don't contain any tuples, you know or basically the range of tuples that are in these blocks, they can't contain tuple Vadodara. So that's why the index scan using bin index for city name Vadodara can skip blocks 2 and 3. Whereas if you're looking for a city called Jaipur, since Jaipur fits in all these ranges, you'll have to scan the entire table. So that's why it's important that if you are using bin indexes, it's your heap or your main table should better be clustered, right? If you are at least nearly clustered. In that case, the bin summary information is quite accurate. For example, we now I have sorted the entire heap, and now you would see that block number 0 now has a tuple within the range Agra and Coimbatore, and block 1 between Delhi and Kolkata. So if you are now looking for city Jaipur, uh, in the previous slide you would have seen that you had to scan all the blocks, whereas now with clustering, for city Jaipur you can skip block 0, 2 and 3 and only look into block 1, which is very good. The next types are what we call GIN indexes or generalized inverted index. The uh, you know, key characteristic of this particular index is that every heap tuple can be indexed by more than one index tuple, which wasn't the case with B-tree indexes. GIN indexes are very powerful and useful when you are storing a lot of duplicate values. For example, let's say you are indexing set of English documents, and you want to quickly search that which documents contain a particular keyword. So gin indexes, what they do is they'll store the keywords, and they will also store the list of heap tuples where that particular keyword appears. So there is, the gin index has a key and what we call posting list, which is set of sorted TIDs of the heap tuples where that particular key appears. So yeah, I mean, as I said, gin indexes, they are used for uh, even looking up JSON documents using HStore, or let's say you are maintaining integer array, or PG trigram, which is a contrib module to support similarity search. All of these things they use gin very heavily. Hash indexes, they have been in Postgres for very long time, but very recently in PG10 they were made crash safe, and they also started supporting replication starting PG10. So that's why hash indexes have become sort of useful now, even though they existed for quite a long time. Um, the key point about hash indexes is that uh, they only support equality queries. You cannot do any range queries using hash indexes because the tuples within the index are not sorted. Uh, but the good thing about hash indexes is that they are relatively smaller in size, especially when your keys are pretty large, because instead of storing uh, the key itself, it stores a hash of the key. So I've sort of taken an example. So if we build a B tree index on column EMP name and a hash index on column EMP name, you'll see that the hash index is much smaller in size, just 528 kilobyte, whereas the a B tree index on the same column is 4 times larger. Obviously, I have deliberately chosen, when I populated the table, the EMP name was sort of pretty large in size. Uh, but as I said, they are good for equality searches, but you can't do anything else with hash indexes. You can't do any range queries with them. Uh, GIST indexes, GIST stands for generalized search trees. So it's sort of, a indexing method which, not very standard, but it's very flexible. So you can, if you want to define your own indexing method, GIST is something that you would most likely look at. So GIST doesn't define any order within pages, but the upper level of the tree uh, has to sort of store correct information about the leaf pages it is representing. For example, let's say you are building an index on geometrical points. Uh, so then the upper level of the index uh, would tell us that this particular index page contains all points within a particular bounding box, so that when you are looking for points within a particular region, or uh, near to a given point, you can use gist index to look up that information. I don't think we have much time to get into details here. So I'm gonna basically just give you an overview that this is gist indexes are mostly used for GIS queries, which is geographical queries, or bounding box queries, or nearest neighbor queries. Evaluating indexing strategies. So how do you know if if your database system is using the right kind of indexes. Postgres has certain system tables like pgstat user tables and pgstat user indexes, where it maintains statistics about tables and indexes, and you can use that information to find out if your queries are using the right indexes or not. You can also look at modules like pgstat statements or pg auto explain, or even just set log min duration, which is a cut parameter to sort of log queries which are taking longer than a certain threshold, and use that information to find out if anything is wrong with your database. But remember, sequential scans are not always bad. So just because you see sequential scans doesn't mean your database is doing poorly. So here is an example. Let's say I run a pgbench query, which is standard tool in Postgres, and I suddenly find that the transactions per second is pretty low. I mean, that's very bad even for my laptop. So how do I investigate this problem? So maybe let's say I start looking at logs, and I have set log min duration to some value, and I see that there is a particular query on a table which is taking too long. So I go and start looking more information. So let's say I query the pgstat user tables, and suddenly I find that the number of sequential tuples, or tuples read by sequential scan for bench accounts table is pretty large. Even for tables like bench tailors and branches, we are using sequential scans. But the odd thing about pgbench accounts is that for just 434 scans, we have read so many tuples, which is like almost 500,000 tuples per sequential scan is what we are reading, which is odd. So with this information, I can start investigating and see whether the what kind of queries I'm running on accounts table, and whether it has the right set of indexes. And yeah, I mean, I found that, looks like someone accidentally dropped. Obviously, no one would do this, but let's assume, someone dropped the primary key or the unique index on the, uh, the column on which we are doing the queries, and that's why suddenly planner or executor is using sequential scans on this table. Once we add back that particular index, now the TPS has at least gone up 200 times, which is good. So, it's sort of important to look for missing indexes and build them, because that can help you improve uh, query speeds significantly. It's also important to look for unused indexes. We sometimes what happens, we start building indexes on every column, but they are never used. Now this is bad, because unused indexes is they not only consume disk space, but they also slow down the inserts and updates operation, and even vacuum operation. So how do we find unused indexes? Again, the system stats are useful there. For example, in this case, let's say I build an index on PA on the PG benches balance column, which I know nobody is querying on, but let's say I build an index and run PG bench for a few seconds. Now I would see that if you look at the second table, you would see on PA balance index there are 0 index scans, and that sort of is telling me that there is something wrong, and this particular index is not being used at all by my workload. So I should look at carefully and see, and whether I really need this particular index. And if I don't need that, then I should consider dropping that index, because that will improve performance for other things that I'm doing. Now, what you need to be sort of mindful is that if you have a replication setup, um, then what can happen sometimes is that a particular index is not being used on your primary, but it might be used in your on your standbys or cascaded standbys, because for example, let's say you run your reporting queries on your standbys. So before you drop indexes on the primary, make sure that you also check your standbys and your cascaded replicas, and make sure that the index is not used there as well, and then only go ahead and drop it. So that's everything that I wanted to cover today. This is the summary. B-tree indexes, they are good for equality and range queries, whereas hash indexes, they are good for equality. They don't support range queries. Brin indexes, very useful for very large data. They support equality and range queries, but they are lossy indexes. So the selects are generally slow, unless you, and it's important to ensure that your heap data is clustered to take maximum advantage of Brin index. Gin is pretty useful when there are many duplicates, and gist is for bounding box queries or pretty much everything else that the other standard indexing methods cannot support. Always analyze your slow queries and look for any missing indexes, and having those indexes can speed up your queries. But remember, sequential scans are not always bad. um, Look for unused indexes as well, because they slow down inserts, updates, and vacuum, uh, and consider dropping them, keeping in mind you should look at your hot standbys and cascaded replicas before you do that. And vacuum can benefit index only scans. So if you think that your table or your query should be using index only scans and it's not, uh, check if you need to vacuum that particular table. I think that's all I have. I think I'll hand over the screen and to Umair, and then we can take a few questions after that. Umair, over to you.
Thanks, Pavan. Thank you for the insightful session. Um, I will take a minute to go through an introduction to Second Quadrant. Second Quadrant, of course, is the organization behind these series of webinars that the attendees are now a part of. Let me just quickly start this off. So yeah, my name is Umair Shahid, and I head marketing and products for Second Quadrant. And just to quickly go through some of the stuff that Second Quadrant does and the introduction for Second Quadrant. We are major contributors to open source PostgreSQL. You can see some major features going into all of the major releases that have come in the last few years. Some of the highlights I've mentioned in this slide over here: logical replication was contributed by Second Quadrant in Postgres 10. This is the latest release that came out. Before that, it was 9.6, and parallel aggregates was a major feature that came out as part of that release. Of course, Pavan talked about PostgreSQL. He is the grand master behind Excel, which is 9.5, and then multi-master replication came out in 9.4. 9.0 saw hot standby, and 8.0 saw point-in-time recovery. There are lots of other features and contributions from Second Quadrant, but these are some of the major highlights. There are a total of 5 core team members of the Postgres community in the world. We have one of those core team members, Peter Eisentraut, and we also have 4 committers on the team. So if we look at the Postgres community, not everybody has the right to commit patches, to commit code. Only recognized and very senior members of the community can actually do that. We've got 4 of those committers, and we've got 17 major contributors to the community. That makes us the thought leader for Postgres development, which means that pretty much all of the major features that you see coming out in Postgres year over year, Second Quadrant will either be the contributor or would have played a major part in those features. We are recognized as major sponsors of the Postgres project by the community, and Second Quadrant is the only company to have contributed major features in all of the last 13 releases that have come out from the Postgres project. Well, on the face of it, you could go and say, who cares? And I'll explain why you should care. You want to rely on someone who knows the project inside out. The people that contribute to open source Postgres in Second Quadrant are the same people that provide you support and other services for Postgres in your production environment. Because we contribute so extensively, a lot of code written in open source Postgres is contributed by Second Quadrant. There's nobody in the world who knows open source Postgres better than we do. And that allows us to give you a guarantee that no other organization can give, and that is for a 24-hour bug fix in case you encounter a bug in Postgres. No other company can provide you with that guarantee. And that's not all. We are a very global organization. We've got presence in more than 20 countries across the world. We've got operating companies in USA, UK, France, Italy, Germany, Ecuador, Australia, and India. We support customers on 6 continents, and the only continent that we leave out is Antarctica because, well, penguins don't really use Postgres. Once they start, we'll probably provide them support as well. Our production support is the signature service that we provide. Our slogan is that when it's critical, you can count on us. A live person, a Postgres expert, is going to respond to you within 15 minutes, and a workaround to your problem is going to be provided within 4 hours. And I just talked about the bug fix within 24 hours. These are guarantees that our production support provides. I've added a quote from the CIO of Fidelis, who's one of our customers, in here. It's something that I'm rather proud of. He says that the Second Quadrant support is always committed to the best answer, not the first answer. So we're not going to go and say, have you tried turning it off and on again? We're going to get to the root of the problem and help you fix it very quickly. Another service that we offer is remote database administrators for Postgres. In case you need help extending your existing capacity, or you don't have existing capacity for Postgres, you can rely on our remote DBA services. And still, that's not all. We have some popular tools that Second Quadrant develops for making up the ecosystem around Postgres. Of course, the database cannot exist in isolation. It needs tools in order for it to be able to run properly in production. We've got Postgres PDR, which is multi-master replication for Postgres. We have PG Logical. BDR, of course, uses logical replication, asynchronous logical replication, and we have made that part available separately as an extension as well under the name of PG Logical. Rep Manager is the management tool for high availability and auto failover management. It simplifies the administration and management of your Postgres clusters. We have briefly touched on PostgreSQL, which is horizontally scalable Postgres. It is fully ACID compliant, and you can use it for OLTP and OLAP workloads. Barman is our tool for backup recovery and backup strategy and disaster recovery. You can get incremental backups, and you can get parallel copy for backup and recovery. OmniDB is a browser-based lightweight tool for interactive management of your database. It is very easy to manage. It is very intuitive. You can edit SQL. You can debug SQL. There's lots of features, and it's a very active project with a new release with new features coming out pretty much every month. That's it from the introduction perspective. I guess you can. I'll leave this slide here. You can contact us for more information. You've got the website URL. You have the blog URL over here, and you have the email info@secondquadrant.com in case you want to find out more. So coming back to the session, and coming back to the questions that some of you might have asked. Pavan, there are a few questions that have come in, and perhaps we can go through them one by one, spend a few minutes talking about those. The first one is there any way we can force the planner to choose a specific index?
Um, so there is no way to do that. I mean, there are some guts where you can basically turn off sequential scans or index only scans, but our experience has been that uh, it's not the best way. I think, if you think that a planner should be using a particular index and it's not, then I would recommend that you should look at stats. Maybe, your planner is not uh, collecting enough stats. So there are things like increasing default statistics target so that, planner gets more sample data and your queries are improved. Sometimes it's also necessary to rewrite the query, uh, uh, but we don't have things like planner hints, etc., uh, because Postgres project feels that that's not the best way to address the situation.
Okay, okay. So the next one that we have is, hello, I have a question about duplicates in B tree. Pointers to heap is sorted? Thanks. Um, you get, yeah, good.
Yeah. Yes. The when there are duplicates um, in the heap or in the index, the TIDs will be sorted. Uh, you know um, the access to the heap would be sequential within that particular uh, you know domain of key. So yes, answer to that question is yes.
Okay. Hi, Pavan. Thank you for the session. Can you please help understand how auto vacuuming slash vacuum affects indexes?
Uh, the so what happens is when you do updates and deletes to your main table, uh, Postgres would never go to the index and delete those index tuples. So the visibility information is in the heap, uh, and we don't during the what I would say online operation, we don't maintain the index. The maintenance of index is the responsibility of vacuum and auto vacuum. So if there are a lot of dead tuples which get accumulated, uh, what vacuum would do is it will go and collect that information from the heap and then go and delete those tuples from the index. So in that way, uh, vacuum auto vacuum is essential to maintain the index. Now there are some, this is not like the a very correct answer in a sense that during the online operation we try to do some index management, like when we see that the heap tuple to a particular index pointer is dead, then the engine would mark that index tuple as dead too. But that's sort of by chance and not by sort of um, uh, with a specific plan to remove all dead pointers.
Okay, okay, thank you. Next up, we've got how do I choose between multi-column index and multiple indexes on individual columns?
Well, that's interesting one. You got when you build an index on multiple columns, what you are doing is basically you're going to benefit queries which say have equality operation on the first column of the index, and then the range query on the second column of the index. That's the only time when the multi-column indexes would be useful. Um, So if you do a equality query on the second column of the index, then the index will not be useful. On the other hand, if you have, you know, multiple indexes on different columns, and then you have, say equality or range queries for uh, for different columns, then what engine can do, or it can basically collect information from these multiple indexes, combine that together, and then decide what is the final set of heap tuples that we should be fetching, and then get that information. So yeah, I think, depending on your queries, you might either be benefited by multi-column index or multiple indexes.
Okay, thank you. So one last question here. If I want to clear bloat on index, is it a good practice to create concurrent index, then drop the bloated index?
Yes, and that's what we typically use as well. I would suggest that, it's a good idea to periodically check for index bloats, and if it has gone beyond a certain proportion, then consider building a similar index using create index concurrently, and maybe rename the old index and drop the index. Now, the only thing that I would want to add here is that, it's normal to have some bloat in the index, and uh, that's not very bad, especially if you do periodic updates and inserts to the index, because uh, that free space in the index would get utilized for those inserts and updates. So it's okay to have, and actually maybe beneficial to have some free space within the index. But if it goes beyond threshold, maybe it's more, say the bloat is more than 70, 80, or 100%, you might want to consider rebuilding that index.
Okay, great. So I think this brings us to the end of the questions list and pretty much the end of this session. Thank you very much, Pavan, for conducting the session and sharing your knowledge. Thank you very much to all of our attendees who came in and listened to Pavan talk about the indexing. In case you have any further questions, in case you want to find out more, you can write to us at info@secondquadrant.com. You can also write to us at webinar@secondquadrant.com. Till our next webinar, thank you again and have a great day ahead. Bye-bye.
Bye. Thank you so much.